Hi everyone, this is going to be the proof of the cubic approximation I introduced in the video, Introduction to Linear Approximation and Beyond. This is going to be an example, to degree 2, nothing particular about this cubic part. You can just extend this proof to any higher order approximation. The linear approximation is usually introduced right after the derivatives are introduced, but the proof of this approximation theory here requires a little bit of integral theory, but not much. So soon as student learned a little bit about integrals, definite integrals, this is understandable. So let me review some facts about integral. If you have alpha and beta, these are two real numbers used as the limits of this integral here. If there is this functional inequality, f of x and g of x, f of x is always less than or equal to g of x, then the action of this integral preserves this inequality. So if you sketch the picture, especially the situation where f of x and g of x mixed sign, this is negative and this is positive, both negative, negative, those are the things that you have to be careful and sketch the picture and make sure you understand this situation. Or if you use the Riemann sum definition, and this is quite clear. And the next part is an interesting part, and this is known as the integral version of the mean value theorem. Now we have these two limits for the integral, and it says if you look at this quantity, so if you know the antiderivative and stuff already, you can look at this as the difference of the two antiderivative, values of two antiderivative, and this beta minus alpha. So this is really the quotients of difference. So here's a difference divided by another difference of input. So you can look at this as a quotients of difference, or slope of the tangent line of the function which is antiderivative of f of x. In that sense, this FC kind of thing makes sense. This is exactly mean value theorem for the antiderivative of f of x. But the proof can be different. Proof actually does not use, the simpler proof does not use, that there is a proof that does not use existence of antiderivative. So which is what I'm going to show. So here's the proof of this item number 2. First we start with the statement in between alpha and beta, by extreme value theorem, there is a maximum and there is a minimum, denoted by capital M and little m there. So all the function values is in between these two maximum and minimum values. So this inequality doesn't matter if little m and capital M are positive and negative, but I'm using here a picture where these two values are positive, and this gamma 1 and gamma 2 are in an arbitrary order, but I wrote gamma 1 here and gamma 2 there. Gamma 1 takes a maximum, gamma 2 takes a minimum. So this is a sample picture to explain this situation, especially to link to this inequality in the areas, especially this one here. Integral from alpha to beta f of x dx, that picks up the area underneath the curve, and especially it's a net area, the signed area, so that's why you have to be careful when you argue using the picture, but this part's clear. So when you have this inequality for all the x's, if you believe the earlier statement that we just reviewed, not the item 2 but item number 1, if you have this inequality, and this is not a function part, this is a constant part here, that's a constant part, and if you think about the Riemann sum, or the definition of the limit of the Riemann sum is this definition of a definite integral, and if you think about that, and this summation definitely preserves this inequality. Especially here we use this fact that alpha is actually strictly less than beta. If you think about it, if it is an opposite order, you can think about simple example. If this beta is less than alpha, then it picks up a negative number, the inequality is no longer true. So you have to be careful. It's very pleasant that you go from here to there just putting those symbols there, and sometimes it's not that simple, so you have to think about it. But alpha is less than beta, m is a constant and the other m is constant. We have this identity all the time while x varies, and we definitely have this inequality results. But one is actually motivated by this to come up with this type of inequality by looking at the picture. So here's an interpretation. So don't think that this is actually the proof of this one is the Riemann sum and the fact that alpha is less than beta. But you can understand this statement using the picture there. This is the minimum, and that's the minimum there. And what this one represents is the area of this rectangle, which is always, this region here is always beneath the region we're trying to calculate. And this one, M, is the highest point there, and therefore this measures the area underneath this highest bar. So this is big rectangles, and obviously if these are all positive, f of x is positive, and little m is positive, and capital M is positive, it's easy to accept that this is true. Again, if one wants to use a picture, there are several other cases to consider, but if you look at the Riemann sum and use the fact that alpha is less than beta, here to there, it's more straightforward to conclude, easier to conclude. So we have the statement. The next part's interesting. So I divided this one I calculated. So I calculated this, but this is since m is constant, this is m times beta minus alpha, obviously, and that part m is constant. So m times beta minus alpha, those are the numbered. So we have very rough an upper and lower bound of this quantity of interest. An interesting part is as we divide both sides by beta minus alpha, we have this beta minus alpha is a positive number, so we have this inequality. And this statement, although it looks complicated, is the following. These capital M and little m is the function values, and we realize this quantity here is actually intermediate value of this function value. And if we assume f is continuous function, f value changes from the little m to capital M continuously, and it's going to go through this value no matter what. That is known as an intermediate value theorem. So this intermediate value of this two function value will be achieved. There will be some function value fc such that this is exactly equal to each other. So here's a statement. That whole quantity there must be exactly some function value for some c that is actually in between gamma 1 and gamma 2. That's achieved as a gamma 2, and that's a gamma 1, I think, whatever this order is, if it swaps. And so this is not so general statement, but I should say c is in between gamma 1 and gamma 2. So that is the proof. And you can see I did not think about any antiderivative or anything. It is just an intermediate value theorem that acquires this value there. So that concludes the proof. So before we prove the cubic approximation, let me remind you of the statement of the cubic approximation. The function f of x often is difficult to compute, the value of which, to say, is actually can be computed as a value this much is the cubic polynomial, so that involves only basic arithmetic. If these values of the first derivative and second derivative and third derivative is available, if you have already good computation of that one, rest the part if it is close enough to a, and those values are approximated nicely by this cubic polynomial here. And this is exactly the shape of the error term, where there's this large order, degree 3 order of the vanishing, and there's another factor of a functional part that also vanishes, becoming 0 as x approaches a. And in the earlier file, I clearly explained the meaning of this thing being approximate, the sense of the good approximation here, which is all actually shown in this, the shape of the error term. So any function here, as long as it's 4 times differentiable, actually 5 times differentiable, so that the fourth derivative is a continuous function in a neighborhood around a, then we always have this result. I already said that we required 5 times differentiable, but the result I stated in the file Introduction to Linear Approximation and Beyond, I assume the infinite differentiability around that point A. So we have this thing differentiable, therefore this fourth derivative is continuous. So we start from approximating this function using maximum and minimum, which is guaranteed because it's closed interval alpha and beta. Let's say we have alpha and beta that contains that little a, the point of interest we're calculating. I mean, it's the points around the neighborhood. So we have this maximum and minimum by extreme value theorem. So we have this rough estimate. So starting from here, not knowing much about anything else about the function, we still have very nice approximation. Just doing from here is the using integral to estimate all the way down to the original function. So that's the idea. Let's look at the first one. Like the proof of the item 2 that we reviewed, it's the same technique. We're going to hit this inequality with the integral. Let's be careful here when you hit this integral, and this integral remains true when this upper and lower limits of the integral is in the correct order. So we have to require x is greater than or equal to a, then we easily argue. Otherwise, these two have to swap around. So it's not much difference. It's still in here and there. So although we're writing the statement x greater than or equal to a, we leave the possibility that if x is less than a, the only difference is that this might go here and that might go there. So stating like this, but aside we have the statement that it's still like this. And at the end, it's not that complicated possibility to remember, so we can just easily state at the end this inequality remains true for not only for x greater than or equal to a, but less than or equal to a. We have a similar statement or something like that. So this is it, and like we did before, we're going to do this calculation in here and there, and because the inside integrand here is a derivative of something, we can use different notation. Let's see, which is this. This one is m is constant, therefore is m times x minus a. It's capital M times x minus a. And here you can see if x is greater than, less than a, we must switch this around because it picks up a negative number. But this part here, using the antiderivative fundamental theorem of calculus, you can write this definite integral as a difference of the values of antiderivative of this one, which is third derivative, of course. So this is a statement like this. Before, we have a function and we have an upper and lower bound. The only difference here, we have actually non-constant part. The lower limit is a non-constant part, an upper limit is a non-constant part. And this is true for all the x values. So if we switch the statement to t with a t minus a and t there, and that's the variable for integral, so I think that's acceptable. As long as t is greater than or equal to a, this statement remains true. So we'll use t as a dummy variable for the next level of integral. So we're going to hit this integral. So if you hit another integral here, and this is what you're going to get, we put this, change this x to t, because that's it holds for any x. So you can switch to the integral variable t, so that's still true, and then you play with this x in the upper limit of the integral. So integral in here, you integrate, because it's a difference of two functions, you can do this separately like this, and then put the integral there. This time, since t minus a is a non-trivial functional part, non-constant part, so you have to go through the integral, and this one we will use antiderivative f2, and this one we'll use, actually this is a constant, there's no t in there, so this will be just x minus a. So here it is, and that part there, if you integrate this one, that'll be x minus 1/2 x minus a squared. And if you evaluated x, you pick up x minus a, evaluated a, you get 0. So that's only, you get that part at m as a constant. If you look at that part, it's the same thing, exactly the same part, except that the little m is capital M, so we get this shape of that tom. And the middle part is, of course, you use the second derivative. Now switch to prime notation. So f double prime of x minus f double prime of a. And this entire thing is, again, this part's a constant, so it picks up x minus a in there. So if you picked up the pattern here you can do from here yourself. Then you have to hit the integral again after you change this main variable to t, and you might get the first derivative version, and if you hit it again you get down to the original version, and that is actually the result. So if you like to do that yourself, you may pause the video and go through the calculation yourself. But if you hit the integral with this x variable after switching that x to t, and this is what you get. Let's see, that part as m over 2 is pulled out as a constant, capital M over 2 pulled out as a constant, and this entire thing with that integral. So that's a functional part, that's a constant part, so it's set aside here, and together with this part is kind of polynomial part showing up. So f double prime of a is a constant, and f triple prime of a, t minus a in there. So this will be just the integral of a polynomial, t minus a plus a constant there. Right, it's a constant, and if you find the antiderivative of this one, it's a 1/3, and t minus a raised to the third power. Evaluate x and a, you only pick up this part, and 1/3 attached to here picks up the denominator on 2 times 3. So from here you kind of understand where that denominator of the cubic approximation is coming from. As you keep integrating this monomial, it picks up this number one at a time and attached to the denominator right there. Same thing in the right hand side, and which looks exactly like the same. So we get this part. So from this main integral part, we have a second derivative as an integrand. So we have a first derivative as an antiderivative, evaluated x and a here. This is a polynomial part, so that picks up t, that picks up 1/2 t minus a squared. Evaluated x and a, again, this at a is going to vanish, so only picks up x part. So that's what this is. F double prime of a constant, t minus a becomes x minus a as you evaluate this in antiderivatives. This part picks up 1/2 x minus a squared. So hitting this one more time, you finally pick up f of x, and that's going to be the approximation we have here. So this part, hitting again that this is general statement for x as long as x is greater than a. So we have x greater than or equal to a, but we have to switch that to integral variable t and hit it with the integral, and this, since this part's constant and pulled out, and the same thing for that side. So it's exactly like the same shape. And middle part, and this is the function with the t part, an unknown part, and the rest of the part is better known as a polynomial. So I separate it like this. This part has this antiderivative, the indefinite integral in t. The rest of the part is a rather polynomial. It's like this. So that treated as a constant. That's a constant times t minus a. That's a constant times t minus a squared. So it's missing dt here, but this will be integrated as a polynomial. So this part's repetitive, so I'm not going to go through each of the part in detail, but that, especially this part now, finally picks up this f of x, and we have some inequality about the f of x in there. The rest of the part is a polynomial with the special values of a first and second and third derivative at a, and the rest of the part is a polynomial. That's very nice, and that's this f of x, and you can see this part right here, including that fa, is exactly cubic approximation, and this tells us then how different this function value is from the cubic approximation. So if you think about it, it came from really the very first estimate of the values of the fourth derivative, and keep repeating the integral. It gives you a nice comparison with a polynomial. Why the polynomial? I think we're keeping this interval xa all the time, and we're playing with this constant. If you integrate constant repeatedly, and that's what happened, you pick up the polynomial estimates. So here's a cubic polynomial. Cx is this exactly this part, and we're going to think about this error part to finish off our proof. So here's a statement with this cx that replaces the cubic polynomial part, and we have this estimate. This difference between this actual function value and cubic approximation is nicely formulated like this. So here's that interesting part that I mentioned in part 2 of the review item. Again, if you isolate this little m and capital M by dividing both sides by this x minus a to the fourth, 24, we get this one. Again, at this stage, you might swap around. I don't know if it's convincing enough that if you look at all those proof up there, and you have possibilities of swapping left and right bound if x and a is in a different order. But here is again, if x is greater than or equal to a, then we have this capital M on the right, but it might switch around if x minus a is a negative, x is less than a. Anyway, this quantity happened to be an intermediate value of little n, m, and big M again. So we have this intermediate value right here. But think about this little m and big M is not the function value of x. This is actually the function value, the maximum minimum value of a fourth derivative value. So since we assume this is infinitely differentiable, here it only requires is five times differentiable so that we can conclude this fourth derivative is still a continuous function. Then we have this intermediate value, realize it as a function value of the fourth derivative. That's an intermediate value theorem. So by intermediate value theorem, this whole quantity right there we're looking at as realize it as the value of the fourth derivative in there. Now if you go back to this statement and there and replace that, actually over here, replace, if you solve this thing for little f of x, and we have the following. It's this one, that's f of x we wanted to approximate using the cubic approximation, and this error term is exactly formulated like this in terms of the special values of the fourth derivative. And the c, of course, that depends on x there, since that's what's in our definition of a c, that's something that makes these two things equal to each other. And as we change this x value, and c will change too. The final bit is rewriting this function as in the shape of our result, where there's this ex. Let me show you that statement. So this is the original formulation. We have this cubic approximation. We want to show the rest of the part can be formulated like this, x minus a cubed part in there, and this rest of the factor approaches 0 as x approaches a. So we're looking at this shape here, and there's a fourth power, so we can leave the third power in here and put these rest of the part together as in e of x. So I slide it up here, so e of x, and that whole thing is e of x now. Let's see if that's a function of x, and of course there's x, and c depends on x, so that looks like a function of x. And as x approaches a, this part is trying to go to 0. As we can show that this one doesn't blow up to infinity, that is a solid proof of this part approaches 0 as well. This is where we use the continuity of this part again. Whatever the c thing is varying in here, and this one spits out the value of the fourth derivative, and is all evaluated c's in between alpha and beta. So this thing is definitely bounded because of the continuity of the fourth derivative in here. So that proves that this whole thing approaches 0 as x approaches a, and that doesn't go to infinity, is bounded by squeeze theorem. One can easily show this part approaches 0. So that's our definition of ex, and it fit into the formulation of a cubic approximation theorem that I showed earlier. And in the proof that I noted here, it's a good remark that it c is not necessarily in between an x and a that you thought. This really came from, c really came from here, the intermediate value of a fourth derivative, and of intermediate value in between little m and capital M. That's not really in between x and a. That really started from the very beginning, started from maximum minimum value of the fourth derivative on this interval alpha to beta. So it's actually in between alpha and beta, not necessarily in x and a. But it's still bounded, so we have that result. So this concludes the proof of this result when x is greater than or equal to a. And the only difference, if you go through when x is less than a, the only difference is the order of the sum of the inequalities back and forth, swapped around, but essentially it's exactly the same. So I'll leave that part for you to examine, but it's this much shows it exactly the sense of the proof of this approximation theorem. So you will see this again. The end of the calculus 2 integral calculus part is introduced as a Taylor series, but this much of approximation is still available, quite available at right after the definite integral is introduced, and it's a powerful statement and a lot of analysis and this much of physics and another engineering. This is an important way of analyzing difficult function to something that we can manage. So I think it's appropriate to this level of approximation is introduced to the students in Calculus 1 level as well. Thanks.